But the next one we come on to is a bit more interesting for us, called GC, gas chromatography. Gas chromatography. Gas chromatography is just simply a method of separating a mixture. Yeah. It's a machine, it's an oven with a long coil in it. So that's an oven. The coil is called the column. And the column is not much thicker than a human hair. Yeah? But it's a tube, about 30 meters long. Yeah? This is what's called a non-polar column. There are different types of column depending on what we separate, but this is the most common one used for perfumery. Yeah?
What do we call it? What was the name that you used?
Oh, a non-polar column. Yeah. So we have an oven which has a really fine control on the temperature. Yeah, this is like really, really important to it. And helium gas is blown down the tube, through the tube. Yeah, it goes round the tube. And just at the top of the column, we have what's called a preheater, which is kept at something like 250 degrees centigrade. And then we get what's called a micro syringe, which is like a little glass tube with a tiny, tiny plunger, just a syringe, with which we can measure maybe one microliter. Yeah, 1/1,000,000th of a litre, 0.001 of a milliliter. And we inject it into our column. So that's our essential oil or our perfume. So as we inject our 1 microliter of perfume, yeah, it goes into this hot preheater and it flash vaporizes. And the helium that flows through our column pulls it down into the column. And if we imagine that our perfume is made of a range of different aroma chemicals or molecules, yeah, what happens is that everything starts to move through together. But some of the molecules move slower. Some move a little bit faster. Some move faster still. And in a non-polar column, generally, that's due to its molecular weight or its molecular size. So what happens is slowly the little molecules form a little band. The medium molecules form another band, and the big molecules another band. Yeah? And as they continue to move, so those bands begin to separate into individual components. Yeah? And they move through the column. And eventually they start to come out the end of the column. And as they get to the end of the column, they go into a flame, which is connected to a meter. Yeah. So if you imagine that the smaller molecules are coming out first, if we remember day 2, isoamyl acetate, that's quite a small molecule. After about 3 or 4 minutes, isoamyl acetate gets to the end of the column. The flame has a little detector on it to detect the ionization, so the positive and the negative charges within the flame. And it stabilizes, because the first 4 minutes nothing's coming out. So the meter doesn't show anything at all. Yeah? Then a material comes out, the material burns, changes the ionization, changes the charge of the flame, and the meter goes ding, 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 yeah, to say that something coming out. So this is then fixed up to an integrator, which is basically a computer, yeah. And as each material comes out, it has a little graph that comes up to say the flame is dirty, yeah. And as that material comes up, the next material in the list starts to come out, goes along. Let's say it comes out at 7 minutes, starts to go up, comes down as it disappears. That's our blue one. Then the green one comes along, the bigger molecules. It comes along, and it comes out. So what we do is we separate each component of the perfume or the essential oil. Now, the time that this comes out is called the relative retention time. RRT, relative retention time. If you control the amount that you inject, the speed of the gas, and the temperature, yeah, to a fixed program, each material will come out at a specific time. Yeah? So the perfumer sits at the end, yeah, and he watches the little graph, and the needle goes up and it says 4 minutes, and then he has a table of materials and it says isoamyl acetate, amyl butyrate, benzyl formate, yeah, and he says, I think it's one of those. Yeah, what's the problem with that? You don't know which one it is. Yeah, so this method called the FID, or the flame ionization detector. This is called the FID, flame detector. Just tells you the flame is dirty, gives you a retention time, and gives you the possibility of certain materials. So if we know this essential oil, we usually have a good idea of what that material might be. So flame ionization detector is the basic GCMS, the GC, sorry. And so perfumers started to say, well, you know, I don't know if it's amyl acetate or amyl butyrate. So then some clever people came along and said, well, how about if we split the column before it comes out, we put a little bit of funnel on there, and we put some silver foil around the funnel to take some of the heat away, heat sink. And we smell it. Yeah? So in the early GC days, the perfumer would sit at the thing, he'd see the needle start to move, and he'd start to sniff. And he'd guess whether it was isoamine acetate or isoamine butyrate. Yeah? And this method is called GC. That was GCFID. This one is GCO. GCO or GC olfactometry. Yes?
How can that work if your material has been flashed at 250 degrees? Surely there's nothing left.
No, it's just a vapor. There's no oxygen there because you've got helium, so there's no reaction. So the components are still complete and undamaged.
The heat doesn't damage them at all?
Well, it happens quite quickly, and it's yeah. Does it damage them at all? Maybe it does. I'm not, but yeah.
They're recognizable.
Yeah, but they're recognisable. Yeah.
Steve,
Yes.
you know, when you say that there's a funnel just before they exit that column.
Yes. Yeah.
So like the vapors actually flow out of the funnel.
Yes. Yeah. So this is called a splitter, and it's designed so that 50% goes up to the FID and 50% goes out to the funnel. Yeah, the GCO. Yes.
3-4 materials will come out at 4 minutes.
Hey.
Yes, it is these 4.
Yes.
Think there are 2 of them in that. So if the perfumer sits at the other end, he'll be able to smell both coming out.
If they're mixed together,
Yeah.
then there's a problem, of course, yeah, because you've got a
Okay,
mixture.
suppose they have
Yes. Yeah.
both.
Yeah.
And both are coming out at 4 minutes. Then
Yes,
what
yeah.
happens?
Then you have a problem. Yeah, and that's why there is an art to the GC, and it costs you more for the chemist than it does for the machine. Yeah? Okay, so but I'll come on to even when we get more sophisticated in this, it gets difficult. Yeah, but what you can do is you can change some of the parameters. So if you were getting the case where you were always getting 2 coming out together, you could maybe slow the gas down, yeah, change the temperature control slightly to get a better separation, maybe make it a longer time, yeah, and that might separate the 2. That's one of the ways. But another way is that you use a different type of column called a polar column, which will then separate them in slightly a different way. Yeah.
I think I missed the point. What is this machine for to separate it? But is it so if you've got a product to find out what's in it?
Yeah.
So it's if you're copying someone for something or
Yeah, if you're copying, if you're doing quality control, yeah. So quite often companies will do this. So they've done their batch of perfume. They will then run it through there, compare it to one that they did the month before, and see if there are any differences between the peaks. Yeah.
If you're a small individual perfumer, would you be doing this?
No, we've got one of these machines is about $100,000. Yeah. So. And then you have, yeah. So we can arrange this service for you. Okay. So that's for separate. Now this is still not complete. So now nowadays we use another detector instead of sending it to the FID or to the nose. We send it to a box, usually a little box on the side. Called the mass spectrometer. As the eluent comes out of the end of the GC, it goes into the mass spec, and it goes into an electron gun. Let me just write that bigger. An electron gun. Through a series of magnets as well, which speed the rate up, this electron gun smashes the molecule into pieces. Yeah? And then those pieces are fed between some electromagnets. Very, very powerful electromagnets, which according to the mass, that means the size of the fragment, yeah, is deflected. And then after they go through the magnets, they go onto a plate. And according to how much they're deflected, yeah, they'll end up on a different part of the plate. And the plate has little electric circuits to detect where the particles hit. And as a result of that, what we get is a mass spec, which is a set of lines like that. So that might be 180, 100, 80, 60, 50. And we get this specific pattern we call the mass spec. And that mass spec is then compared to a database, and it says, looks through all the normal mass spec database nowadays will have a range of maybe 200, 300,000 chemicals. Yeah? And it will compare them to all of those and say, this has a 98% probability it's isoamyl acetate.
So getting back to Turner and this theory of vibration,
Yes.
talks about those being like a gas spectrometry.
No, that was like the first one, the infrared spectrometer.
Okay.
Yeah,
So that's nothing to do with vibration.
no. Yeah, nothing to do with vibration. This is to do with affinity for a particular surface. Chromatography is to do with if the molecule likes the tube more than the helium gas, it moves slowly or fast. Yeah, that's how the separation occurs. Yeah.
Steve, can you please explain this again? What exactly happens after the small particles come down between the magnetic plates?
Yeah. So as they're accelerated through between the magnetic plates, yeah, according to their mass, they're deflected to one side or the other. So this is plus, this is minus. Yeah. One that has more mass has more momentum, so will tend to go more straight. So, yeah, not atom. This is not exactly how it happens, but to get you an idea of what the electron gun does, imagine we have a terpene, yeah, structure. Yeah. What the electron gun does, it breaks it. It breaks it maybe there. So we get this piece. And then we get this piece. And then we get this piece. And then we get the whole molecule. So the whole molecule, we might get fragments of that left. So that's our biggest part of the spectrometer. Then it broke at this part, which gave us a molecular weight of 100. Then it broke at this part, which gave us 80, like that, yeah? So it sort of shatters the molecule. Then that pattern that you get becomes specific for that molecule. Oh. Does that make sense, or? Yeah.
This basically has, like whatever molecular weight a particular particle will have, the deflection and where exactly it hits the surface.
Yes.
Will depend on the weight.
Yeah, on the molecular weight, the mass, yeah.
And mostly all molecules will have different weights.
Yeah, that's it. Well, not only that, even if they have the same weight, they may break differently, yeah, according to where the weakest point of their structure is, yeah. So they break into different fragments. So even though you get two molecules exactly the same weight, according to where the double bonds are, they will break in a different place. So that will give you a slightly different pattern, and that pattern is matched to the database of hundreds of thousands of raw materials. Yeah.
That is again all computerized, all the matching.
Yeah, you couldn't do this without computers. Yeah, it'd be impossible to do without computers. Yeah, it wouldn't mean anything. Yeah.
But there are still ingredients which even this technique would not detect.
It has a weakness. There are two things. The two things that it has a weakness for. One is if the molecule can't be vaporized. So furocoumarins, the ones responsible for phototoxicity, yeah, are actually quite hard to do with GCMS because they're fairly big molecules, and they don't really want to go around the column at all. Yeah. If you get non-volatile components of absolutes, they sometimes don't want to come out. Yeah. The other thing is that for the mass spec to work successfully, the eluent, the single material that comes out, must be a single material. If it was mixed with isoamyl butyrate and isoamyl acetate, yeah, then this pattern would be meaningless because it's got a contamination. So this is where like skill comes in with the experience, yeah, of the chemist, and that's why they earn the money.
How do you spell eluent?
Elute. Or the eluent, yeah. To elute, to eluent.
And if there's a problem with your calibration of this particular thing, then what are the chances that whatever reading you're getting is absolutely wrong?
High.
Very good.
Very high. Yeah. So the other thing is, you see this thing here, you get 98%. You'll never get a 100% match. There is no such thing as a 100% match. Yeah. So it's all done on probability. Yeah. So in this list, it might say isoamyl acetate 98%, and then it says amyl butyrate 67%. Yeah. So there's still a chance it is actually amyl butyrate. Yeah. Now, if you send 3 samples for analysis, one sample will probably be 98% correct. One sample will be about 90% correct, require a little bit of modification, and then one doesn't work at all. One, yeah, because perfumery is a cat and mouse game. Yeah. The perfumer knows that his competitor will put it through a GCMS, so he will try to do things with his compound to confuse the GCMS. Yeah.
Is this where extracts come in?
Yes. Well noted. I wasn't going to say it, but no, you said it. Yeah. So, yeah, the purpose is to, what can you do that adds something to your perfume? It should add something, but it's difficult for somebody else to copy. And basically, all that layering stuff, very difficult to detect with this.
But
Yeah.
why is that so?
Well,
Like yesterday, you led our creations with your X factor.
yes.
If you use something else for layering, it could be detected, right?
Yeah, but if you'd used Rose Otto, which has maybe 300 components at 0.001%, it adds something to the perfume, but in terms of the GC, it's just noise below the threshold. Yeah.
I don't get it. If you add a Rose Auto, like you said,
Yeah.
so what exactly happens when it runs through this machine?
Okay. So that line diagram I did before is called a chromatogram. So it looks like that. So let's say this is a rose perfume. This is phenyl ethyl alcohol. This is geraniol. Probably the wrong way around. Yes, the wrong way around actually. This is citronellol. Let me change that. This is geraniol. This is PEA. This is rose crystals, the rosone. This is cis-3-hexanol. This is, what could that be? Amyl acetate. And dimethyl octanol. Okay. So this basically makes up 100% of our perfume. Now, if I add 0.001 of Rose Otto to it, it has like 300 peaks. So if I put Rose Otto through the GC, I'll get like 300 of these. Yeah, very, very tiny ones, and reasonably big ones. But these materials, this one, and this one, are actually in Rose, the main ingredients in Rose Otto anyway. So when I add 0.01, what I'll get is like this. I'll get something like that. The main ingredients will show up as, could be synthetic or could be natural. These other ones are so small that unless I'm specifically looking for them, I would never find them. And this is like any analysis. When you start to analyze something, to do this basic analysis, 45 minutes on a GCMS. Yeah. Chemist uses maybe an hour to interpret the results. Yeah. But what if he suspects there's Rose Otto there? Now he then has to change all the parameters, reset the machine, yeah, to look for specific markers. Yeah. And what that means is that it may cost, it may have to do 5 or 6 runs. So now the cost of doing it has gone up 10 times, yeah? And then he may have to put a new column in there, and then it goes up again, yeah? And what you end up is with what they call the law of diminishing returns. It becomes impractical to do because it would be so expensive to detect these materials, yeah?
And Steve, when you run a GC,
Yes?
does it happen that some of the molecules or whatever ingredients, the vapors might remain in the column? Does that
Yes, yes. And so every so often you do a flush. You run the GC without anything in there to try to flush the materials out, and you'll overheat it, yeah. And that shortens the life. So it's, yeah. So like Ryan asked me, how many runs can you do? It can be a piece of string, because if you're like really fussy about cleaning the